Good day, everyone. Today we're gonna be solving a physics problem on kinematic equations. So we're gonna be using the kinematic equations to solve the skier problem, which, well, many find difficult. So for this problem, we're gonna have to solve for the distance d at which the skier lands on. So you may probably, you can probably visualize this one. So for some time, the skier would have landed on the platform that's angled at 50 degrees from the horizontal axis, as you can see. Okay. May try to draw this one, or we may try to visualize this on the coordinate planes as like this, which this case will have the positive y going that way, positive x going this way, and then the ramp, which I'll put in the origin. Oh, this is the platform rather. So the ramp. So the point at which the skier leaves the ramp is my origin. So that's my origin. And so the skier leaves at an angle of, let's just approximate at 15 degrees, somewhere that way. So that's going to be our initial velocity vector. Okay, more about that later. So this is 15 degrees, and we know our platform below makes an angle of 50 degrees from the horizontal axis. So this is referred to as the angle phi in the problem, and the 15 degrees is referred to as the angle theta in the problem. So the skier leaves the ramp and lands somewhere on the platform, which, let's just say, coincides with the delta x that we're gonna be finding later. So that makes delta x, which is the change in the skier's x position, or that is his displacement on the x-axis of delta x, and delta y, which is the displacement made in the y-axis. So that's the difference between its final position and the initial position. And let's talk about the the signs of these changes. So for delta x, we know that since the velocity is going towards the positive direction, positive x direction, the initial velocity is going towards the positive x direction, then we know that delta x is positive. Whereas for delta y, we know that it's going to be negative because since we set our origin to be at the point at which the skier leaves the ramp, then this will become negative. Okay, the velocity in the y direction goes towards the negative y direction. And so, as you may have probably seen, what we have here is a perfect right triangle for us to uh, start the solution with. Okay, so let's see this. We know that the skier will land on the distance d from the origin on the platform. And in order to find the d, we can use, well, the Pythagorean's theorem, or we can use the sine and cosine functions to find the letter t. So in this case, let's start our solution with delta x. And since our delta x is adjacent, it's adjacent to the angle phi, then we know we can use the cosine function here. So we'll have the hypotenuse d times the cosine of phi. Okay. So let's start with this one first. Okay, because where else can we see the delta x from? So we know that the delta x is also equal to, well, it's already here. We know that our position is the same as the product of velocity and time, and that is the same for the initial velocity in the x direction. So we'll have for the delta x, we'll have v xi times t. But what is vxi? What is the velocity component in the x-axis? So we know that our initial velocity is a vector in which we can dissolve. So let me just zoom that one in. So this is a velocity. So our velocity is a vector that we can dissolve into its x and y component first to find vxi and vyi for that matter. So let's name the component in the x-axis as vx, or the initial velocity in the x direction, and the y component as vyi, as the initial velocity in the y direction. Okay. And so, since we have an angle, since the velocity vector, the initial velocity is angled at 15 degrees, and our vxi is adjacent to it, we can see that this is equal to the magnitude of the initial velocity cosine of theta times t, where that is our delta x is equal to 10 cosine of 15 t. Okay, now we can use this to equate to our first equation here, d cosine phi, and we'll have d cosine of phi is 50 degrees, then we'll have 50 degrees. Okay, and what we have here is an equation in which two variables are missing, the t and d. These are the variables t and t. So we need another equation in which t and d are also missing, so we can solve these missing values. And for that one, we can use the delta y, which in this case, since this is a free fall motion, then what we'll have here is, to find the delta y, we can use this equation up here, which will give us the final y position. So using that one, we can have the initial velocity in the y direction times t minus 1/2 gt squared. Okay, so that seems perfect because we have the variable t in here. Okay, so all we have to do now is to find what delta y is. And delta y, as you can see, is opposite. So it's opposite to the angle phi. And for that part, we can use delta y equals, and take note that it is supposed to give us a negative values. It will be negative d sine of phi. So we have the sine of phi as sine of 50. So we'll have sine of 50 degrees. And substituting that to our equation above, we'll have negative d sine of 50 degrees is equal to, so for the vyi part, we already know, or we already know that the x component of our initial velocity is vxi, that's equal to vi cosine theta. So for the vyi, okay, vxi is equal to the magnitude of vi times cosine of theta. So the vyi will give us the magnitude of vi times sine of theta. We're just gonna have to use that value for the vyi here. You'll have vi sine of theta times t minus 1 half gt squared. Okay, and we'll have, substituting all the values, we'll have negative t sine of 50 degrees is equal to, our vi is 10, sine of theta is 15 degrees times t minus 1 half gt squared. And so we found our second equation, which also has the d and t missing, or as the missing values. So you have d, and then for the t, we have t and t squared, so that makes a quadratic equation. So let us just call this one equation 1, and this one is equation 2. So you may choose to solve for the d first or the t first. That depends on you. But for this problem, for the sake of simplicity, I guess I'm gonna use the equation 1 to solve for the letter t, and then substitute that to our equation 2 here to solve for the value of t. And then afterwards we can find what t is once we found the value for t. So let's try that approach. Let me just rewrite equation 1 and 2. And we'll have, for equation 1, it's 10 cosine of 15 degrees times t is equal to d cosine of 50 degrees. So solving for the t first, so t will give us cosine of 50 degrees over 10 cosine of 15 degrees times d. Okay, so you can use your calculator to find the value of the coefficient of d here, and you can store that to a. For this one, I get a value of 0.0665 with other values. Okay, so now going back to our equation 2, we have negative d sine of 50 degrees, which is equal to 10 sine of 15 degrees times our t. But what is our t? This is our t now, which is equal to AD now, since we stored the value of the coefficient of d to a. So for the sake of simplicity, let's just put a instead of cosine 50 over 10 cosine 15 degrees, because that will make things much easier. And now we'll have times AD. Okay, so we just substituted the value of t for the, so we just substituted the value of t from equation 1 in the second equation, and we'll have minus 1 half g times AD squared, that is t squared, so we'll have AD quantity squared. Now, what we have is this for the second equation, which is just in terms of t. So that makes our d solvable now. We just have to solve for the value of t. And for that part, I guess we just have to simplify things first. So let me just rewrite this one so that we'll have 1 half g times a squared. So distributing the exponent now to a and t, we'll have 1 half g times a squared d squared. And then I've just transposed this to the other side and the negative becomes positive. That is what I'm also going to do with the first term here, tan sine 15 degrees of times AD. And we'll have minus 10 sine of 15 degrees times AD. Okay, but let me just put A here before the sine of 15 degrees. And we'll have 10A sine of 15 degrees minus sine of 50 degrees. So that is this part. It remains negative because it's already negative on that part of the equation. And then moving the d out from here, so factoring the d will give us this term equals 0. Okay, now we have the coefficient for t squared and another coefficient for d, which we can solve for using our calculator. So the 1 half g a squared will give us 0.5 times g, that will just give us 0.0216 21699 and so on, which we can store to b. Now the other term which you can store to c, you just have to store that to c so that we get an accurate answer later. That will give us 0.93827 and so on. So store that to c, and then we can simplify this equation further by having bd squared minus cd instead of that whole thing. Okay, now what we have is a solvable quadratic equation. So it's a quadratic equation, so we may choose to use the quadratic formula to solve for the roots of the d. But instead of doing that one, okay, why not just factor out 1d and we'll have bd minus c, and in this case we'll have, okay, we'll be able to solve it much more quickly or much quicker, and we'll have the first value for t is equal to 0. We know that this is 0 because this part of the platform touches the origin, so that could be our d1, and this could be our d2, the second root of t, and we'll have, you can name that d1, you know, it will equal to 0 because it touches the origin. But for the d2, that is what's going to give us the part of the platform in which the skier lands on, and that is equal to, well, just transposing c on the other side and dividing both sides by d, we'll have c over b, and our c is just 0.93827, and then we have to divide that by our b, which is 0.021699 and so on. But if you have these values stored in your calculator, then you can just directly put c over divided by b on your calculator, and that will give you 43.24027 and so on meters, or that's approximately 43.2 meters. And now we have the value or the distance at which the skier lands on the platform as 43.2 meters. So we can now go back to our first equation. So we know that we have t is equal to AD, and now we have the value for D. And we can solve the time at which this happens. So that's just A times 43.2 meters. So assuming that you have the value of A stored on A, then you'll just have to write A times 43.2 on your calculator, and that will give you a value of 2.8747 seconds, or we can just approximate that to 2.87 seconds. That gives the time to which the skier lands on the platform. And that, I guess, concludes our solution to the problem. So there's another question in which it wants you to find the final velocity, but I'll just discuss that on another video. So thank you for listening.